All right, hello. This is 24A, and chapter 24 is on the normal distribution. So is 24A. The normal distribution only applies to continuous function or continuous random variables only. Oops. Only for continuous random variables. And a normal curve is bell-shaped, so it looks like this. And there are some characteristics about it. So we'll call the function y equals f of x. And by the way, that's called the probability density function. Probability density function f of x. So the bell-shaped curve is the probability density function. And so this is x, and then you could put a y-axis on here if you wanted to. And then the area under the curve is the probability. So for instance, if you had, and the other thing I was going to say is that f of x is always going to be positive, so we'll make a note of that. F of x has to be greater than or equal to 0. So I guess it could actually equal 0. And the other thing too, the probability is the area under the curve. I'll just write that out, I guess. So in other words, the area under the curve, we know from calculus, is the integral from, like say you wanted to know the probability that x is between this value and this value. So say you want to know the probability between c and d. Now notice I had said that this is for continuous random variables only. So you're always going to be finding the probability of an interval, not an exact number. So say you're finding the probability that the x values fall between some c and d values, then you would take the integral of f of x dx. And that would equal the probability of x. Let's see how I think about it. I'm going to make sure I write that right. Yeah, well, it's the probability, here, let's do this, that x is between c and d. How about that? That looks nice. All right, I'm just kind of looking at my notes here, making sure I don't miss anything. If you want, you can look in the book and write up like the formal definition, but it's pretty much this right here. And let's see, for a continuous variable, the probability is exactly equal to a particular value of 0. Oh, yeah, like I was saying, you can only consider the probability that an event lies on an interval. We can't find the probability at an exact point. And one of the reasons is, like if you're doing continuous variables, then those come from measurement. And when you're measuring something, you're using a scale, a measuring device. And a measuring device is only as accurate as, half of its smallest increment. And because when you measure, you can never know exactly an exact measurement. It's always plus or minus half the smallest increment. So if you measured like 32.3 centimeters, you only really know it's going to be between 32.25 centimeters and 32.35, because half of a tenth is a hundredth, or wait, it's 0.05, whatever that is. So anyway, if you're measuring to the nearest tenth of a centimeter, the error is plus or minus 0.05 centimeters. And see how this measurement here is actually over this interval. Okay. Oh, and in nature, yeah, normal curves or data that's arranged, like if you plot it, Sorry guys, I'm a little tired today. Oh, it's been one of those days. In nature, the normal distribution occurs often. And of course, it occurs right in the classroom with test grades. If you have a large class, you're going to have a mean. So, oh, by the way, I forgot to mention that. On a normal curve, the mean is right smack dab in the middle there. And then you're going to have scores that are above the mean, below the mean, but most of them are near the mean. And it'll taper off as you get to really large values and really large negative values. So test scores are something that naturally occur. They occur often in the shape of a bell-shaped curve. Oh yeah, the other thing I noticed right away when I graphed this is concave up, and then somewhere in here it switches concavity, doesn't it? And it's concave down, and then it's concave up again. So somewhere in here there's an inflection point. POI, we could call it POI, point of inflection. There's one over here too. Okay, I think we're ready to move on. So the definition. Oh, okay. Look at this. Check this baby out. Definition. If random variable x is normally distributed, then its probability distribution function. Whoops. Its probability distribution function is f of x equals, and get ready for this thing, it is 1 over sigma square root of 2 pi times e to the negative 1/2 times the quantity x minus mu all over sigma, all that quantity squared. Whew! That is a heck of a function, isn't it? That is the function that describes the bell-shaped curve. And if you're really ambitious, well, you'd have to know a sigma and a mu, right? If you had a sigma and a mu, you could plug that into your calculator and you would get a bell-shaped curve. And that's true, so that's valid when x is less than infinity and greater than negative infinity. And also some other notation is, it says x is distributed as big N of mu sigma squared. I guess that notation goes along with that formula somehow. All right, here are some characteristics. So f of x is the normal curve. Called the normal curve, and it's symmetrical about x equals mu. I mentioned that before. Mu is the mean, and the mean is, why do I always want to draw that anyway? The mean is right there. As x approaches positive or negative infinity, what happens to f of x? It's going to approach 0, isn't it? So that's a limit. And f of x, well, we already talked about this. Oh, it says it's greater than 0. Because on the other slide, it was greater than or equal to. So I should probably consult the book and see which one is supposed to be correct. I think I'm seeing here it says greater than or equal to. And I'm seeing there it's... So the book is contradicting itself. I don't know. I don't know the actual answer. It seems to me like it should be this one, though, because I don't know if it actually ever reaches 0. Who knows? I don't think it really matters that much. Sorry. And then if you integrate from negative infinity to infinity of f of x dx, what are you going to get, do you think? Well, the area under the curve is the probability, and this is over the entire range of possible x values, so the entire probability has to be 1. That brings, oh, and it's bell-shaped. That's the other little thing. The normal curve is bell-shaped. Okay, let's head on into the next slide. This one we're going to get a little more specific. I'm going to draw a nice big bell-shaped curve. We know mu is in the middle. Well, if you were to go back and get that horrendous equation for f of x, and if you were to take its second derivative, which I'm going to spare both you and I the trouble in doing that because it looked like it would be quite arduous, it turns out that mathematicians who have done this have discovered that the points of inflection occur within one standard deviation of mu. So points of inflection occur at x equals mu plus sigma and x equals mu minus sigma. And visually, well, we know it's about right in here, isn't it? So about here and here are our points of inflection. So this is mu plus sigma, because remember sigma is the standard deviation, and then mu minus sigma. This is also a POI. And another POI. And that's kind of cool. And then I'm also going to come out here and do mu plus 2 sigmas. So we're going to go out 2 standard deviations away from the mean, and then mu plus 3 sigma. This thing I'm drawing right here is actually very, very important and helpful, so I do recommend copying this down. This is going to be mu minus 2 sigmas, mu minus 3 sigmas. And it does keep going, really small out here too. So you could do mu minus 4 sigmas if you wanted. But that's not much area. And mathematicians have done the integration, which wouldn't be too hard. I mean, we have the nut technology. We ourselves could actually do that, but that is such a humongous formula, and we just don't have the time to deal with all that. They have discovered that from mu to mu plus sigma, this area right in here is 34.13% of the distribution. This area is 13.59%. This one is 2.15%. And since it's symmetrical, you have the same deal here on the other side as well. And 2.15%. What this all boils down to is that if you look at the area, so we're often curious, how much of the data is within one standard deviation of the mean. So that's from here to here. Well, all we have to do is add up the 34.13s, double those, So what is that? That's 68.26. So 68.26% of the data lies within one standard deviation of the mean. Okay. One standard deviation of the mean. That is super important to know. And I didn't get around to looking at the formula sheet to see if that's on there, because if it isn't, we're going to have to memorize it. And then if you look at within 2 standard deviations of the mean, so if you add up 13 ... these 4 numbers here, you're going to get that 95.44% of the data lies within 2 standard deviations of the mean. And if you go to out to 3, which is almost the entire thing, isn't it? That's 99.74% of the data is going to lie within 3 standard deviations of the mean. So there's just a little bit left out here on the very, very edges. And my favorite mathematician, Gauss, actually was the first one who used the normal distribution. And apparently he used it to justify the least squares regression method. So he must have perhaps came up with the least squares regression method as well. Not to mention, remember the sum of the arithmetic sequence. Plus he did a bunch of stuff in calculus. Physics is what I meant to say. He was amazing. Well, cool. Now let's move on to our example. Yeah, these numbers here, I even remember using these in college a lot. So this is super important to know that stuff right there. And then this table, this picture is very helpful as well. Now we're ready to do our example, our one and only example for this section. Which means I have to find it and read it. I didn't have time to prep the slides ahead of time. The chest measurements of 18-year-old male footballers are normally distributed. So notice these are measurements, so it's continuous. with a mean of 95 centimeters, so that's important. We'll write that down. And a standard deviation, which is sigma, of 8 centimeters. Find, of course, automatically, you know what I want to do. I want to draw a picture. I just love drawing pictures. Bell-shaped curve. My mean is at 95. See, already, automatically, I haven't even looked at the problem, and I just want to sit here, and I want to put my little sigmas on here. Got to move this thing out of the way. Oh, there's a way to get it stuck down there, but I pin it. There. Okay. 95 plus 8 will give us the next one, so that's 103. And then 8 again, 111. And then, let's see, that's one standard deviation, 2 standard deviations, so it goes out some more, 3 standard deviations, so plus 8 again. And then minus 8 is 87. And then minus 8 again is 79. And then minus 8 again is 71. See, now I can just look at this and I know from 87 to 103 that data is within 1 standard deviation of the mean. I already know the percentage too because I just talked about that. So I know that 68.26% of the data is between 87 centimeters and 103 centimeters. Well, let's see what the question's asking in any case. Find the percentage of footballers with chest measurements between 87 and 103. I just figured that out because I was so excited and I went here to this thing and I already know this. So I that's within 1 standard deviation. That's 68.26%. Now since it's IB, we best round that to 3 sigs. So there. Second one. Between 103 and 111. Oh, that's this little guy here. Of course, I just made this picture on the other side, so I remember it was 13.59%, right? So if you go back right to here, I'd given us that information as 13.59%. You know, I really ought to go look at that formula sheet and see what they tell you. I wish I'd thought to do that ahead of time. Let me go do that really quickly right now because I have it handy over here. Because obviously on the IB exam, you're not, well, more than likely you're not going to have that 13.59% memorized. So you can't just give that answer. Let me see. Oh, they don't give you anything. You know what I kind of suspect though? Is I suspect there's probably a way to find that on the calculator, which we'll get to in the next section. So for now, the other thing, because I was looking in the formula sheet, they don't even give you these percentages right here. They don't give you these. Okay. And I haven't got those memorized very well yet either. I'm going to write them down here though, because those are really important percentages. My guess is by the time you and I get done with all this homework, we'll probably have these memorized. Say you just knew these, so this is within 1, this is within 2, this is within 3. What you can do is you can use a little bit of arithmetic, and you know that this is 68.26%, and you know that this whole thing is 95.44. So what you can do is you can subtract. You can do 95.44 minus 68.26. That gives you this area here and here, and then you can divide that answer by 2. So that's another way you can get the 13.59% if you don't know it off the top of your head, but if you happen to know these. Anywho, enough on that. Back to my book, which I have to find. Okay, where are we here? Oh, all right, so we're done with A, letter B. Find the probability that the chest measurement is between 87 and 111. Oh, all right. Well, that's really easy too, because that's just the 68.26 plus the 13.59. So it's just adding these two up, and that will be 81. Oh, and I forgot to change that to sig figs. So that's 13.6%. That's the answers we're supposed to give. And then the last one's going to be 81.9, I do believe. Yeah, 81.9% if you add those two together. And then the last question, letter C. Find the value of K such that approximately 16% of the chest measurements are below K. Well, I know this is 13.59, and if I look back a slide or so, 2.15% is right here. Now, could it just be that, let's see, 13.59, that's 13.6, plus 2, this is basically 2.2. What does that equal? 0.8. That's 15.8%. That's pretty darn close to 16. So that means, and plus you have this little bit left out here too. So this plus this plus this, right here is where your K would be. So your K would be 87. And we're done. Okay, so we'll just do this for today. Next time we'll learn about how to use a calculator, and we're also going to learn about the Z distribution. We'll see you later. See you in class.